Go ahead.
Okay. Yeah, welcome everybody. This is definitely the last session of this seminar of the year. And we're very happy to have Marcel Nutz as our first speaker, Stephan Eckstein as our second speaker of the day. Marcel is joining us from Colombia. We're very much looking forward to your talk, Marcel. And please, people in the audience, you can just ask any questions, interrupt if you want, or otherwise you can write in the chat, and there will be hopefully time for discussion at the end of the talk.
Okay, thanks so much, Julio. Thanks for the invitation. Thank you everyone for joining for this talk with a slightly cryptic title. I'll explain what it's about. This is joint work with Chen Yangzong, who's a postdoc at Columbia. He's right now in Stanford, so I'm guessing it's a bit too early for him. He's probably the main reason for the progress in this project. This is still ongoing work. You'll see in which sense it's ongoing and what is already completed. So for this talk, there will be a general introduction to optimal transport and entropically regularized optimal transport for the first 10 minutes or so, and then I'll jump to the main part, which is this entropic selection problem. So many of you will have seen the optimal transport problem, but maybe it's good to bring everyone to the same page. The original formulation of the optimal transport problem due to Marsh looks like this. You have two spaces, X and Y, which are both going to be RD. And you are given two probability measures, mu and nu, on that space or on those spaces. And in addition, a cost function, C of X, Y, which tells you what is the cost to bring a unit mass from location X to location Y. Okay, so we think that we are given one probability measure, which is the origin, the mu, and we want to say this is a sand pile. We want to transform it into another sand pile in a different location, in a different shape, nu. And in Morse's formulation, we do that by means of a transport map T. Okay, so what T does is basically it picks up all the mass from some location X, let's say this is little x, and it brings it to some location T of X. Okay, so mathematically it means that mu is pushed forward by T into nu, or the equation that's stated here. So if I think of T as a random variable, and under the probability measure mu, its distribution is exactly nu. Okay, so those are the maps which transform one sand pile into the other. And then the goal of the problem is to minimize the transport cost over that set of maps. The transport cost is simply for each location X, you bring the mass to T of X at this unit cost. So it gets multiplied with the mass located at X, and then we sum up those costs over all locations X to give the total transport cost. That's what we try to minimize. And for this talk, the Kantorovich formulation will be more important. So this is a relaxation of the original problem where instead of bringing mass from X to Y, you can pick up the mass from X and distribute it over different locations Y. So mathematically, it means that we are looking for a coupling, a probability measure pi on the product space. And the marginals of this measure are mu and nu. And now the cost of a coupling is computed in this more straightforward way. We just integrate the cost function with respect to the coupling. Okay, so this is indeed a relaxation. In general, we can take a coupling and disintegrate it according to the first marginal and a transport kernel. If that kernel is a Dirac at some location T of X, then this coupling corresponds to a Morse map, namely the T in here. Okay, one reason why optimal transport has become very popular are that it gives rise to optimal transport distances. So basically, we can think of this number here, the optimal value, as quantifying how different or similar the measures mu and nu are, at least when the cost function is suitable. In particular, if both spaces are the same space, say RD, then for suitable cost, this would define a metric on the space of distributions on X, often called the Wasserstein distances or earth mover distances. And the two, I think, most prominent, most important examples are these two here. If I take as cost function the distance, say the Euclidean distance on RD, so-called distance cost, then just taking the number OT is actually a metric. So that is the one Wasserstein distance. And the most probably popular example is the quadratic cost. So we take the square distance, then we have to take the square root at the end to make the triangle inequality work. And this is the 2 Wasserstein distance. Okay, so generally you start with a metric on your ground space and you lift it to a metric on the space of probability distributions. This is very heavily used. I'm going to skip this slide in the interest of time. Very heavily used these days in data-rich environments to compare two distributions of possibly different nature. And the one reason that this has become popular is that in the last decade or so, fast approximate solvers have allowed to really compute large-scale problems. Okay, so for those approximate solvers, regularization is a key approach, and entropic regularization is the most popular one. Okay, so the idea is to compute that number OT in a cheaper way, approximately, than by some exact computation. So let me tell you what this entropic problem is. The entropically regularized or entropic optimal transfer problem is this one here. It's the exact same optimal transfer problem in the control-rich formulation that we just saw, but we add a penalty. Okay. So the penalty has two parts. There is the regularization parameter epsilon is just a positive number that tells us how strongly we want to take into account the penalty function. And then the penalty here that we're choosing is the relative entropy or KL divergence of the coupling pi with respect to a reference measure, which I choose to be the product of the two marginals, so mu times nu. Okay, the KL divergence, as usual, it is computed by looking at the log density of the first with respect to the second argument and integrating by the first argument. Okay, as long as that density exists, and if the density does not exist, then the relative entropy is infinite. Okay, so if the coupling is not absolutely continuous with respect to the product measure, this is just infinite and not really informative. I'm emphasizing that because it will be important later on. Okay, so the EOT problem here, this is a linear problem with respect to pi. This is a strictly convex problem with respect to pi. Together, it's strictly convex. It has a unique minimizer that I'm going to call pi epsilon under essentially no assumption. Okay, just need to be finite, then it will have a minimizer that is unique. And of course, when epsilon is 0, you kind of delete this term and you recover the OT problem, which is what's stated here. So in general, we can think of this problem as a trade-off between these two terms. And the trade-off is being modulated by the parameter epsilon. Basically, if epsilon is very large, you just care about minimizing relative entropy. So this function here is non-negative at 0 exactly if pi is the product measure. So when epsilon is large, the pi epsilon should look like basically like the product measure. And when epsilon is small, then this term is not very important and you're mostly caring to minimize this term. So then pi epsilon should look like an optimal transport. How exactly, that's actually exactly the topic of this talk. Okay, so in general, we have this interpolation between the two ends, and these pictures are just supposed to illustrate that. So in this picture, we have 4 similar pictures. In each one, the red and the blue curve are the marginal distributions. They're given. Then we're solving the optimal transport problem here for the quadratic cost on R times R. And so on the left, epsilon is very large, and you see the solution more or less looks like the product measure. And as we go to the right, the epsilon becomes smaller, and you can see that here the pictures are changing and converging to something. Indeed, in this case, we know that for epsilon equal to 0, the picture, the unique optimal transport would be the Brownian map, or in this case, it's also the Frechet-Höfting coupling, which would be concentrated on a graph. So you see here that how this is starting to concentrate on the graph and converge to that particular coupling. Okay, and sort of this limit is what we're going to be interested in the main part of the talk, the limit to the right as epsilon goes to 0. Okay, are there any questions about the basic problem formulations? Okay, then I'll jump into the main part and also slow down a bit. Okay, so we just introduced pi epsilon, a particular coupling, as the unique solution of this EOT problem. Okay, so for fixed epsilon, there's always a unique pi epsilon. So it is very reasonable to ask this question, which is boxed here. What happens with the coupling if I take epsilon to 0? Okay, because epsilon equal to 0 somehow corresponds to optimal transport. You know, it's very immediate to think that this should converge maybe to some optimal transport. Maybe there is more than one, then which one? What would that look like? It's a very obvious question, but surprisingly, there's not that much known about it. I want to just contrast this with another convergence that you can ask. Mainly, you can ask about the convergence of this, the left-hand side, which is a number, okay, the optimal cost. The convergence of this number to the optimal transport cost is quite well studied, and there are many more papers than would fit on this slide. So essentially, the convergence would hold under minimal assumptions on the cost. And there is much more precise information about the rate. The rate will be different for like discrete and continuous problems, depending on the regularity of the cost function. There are higher order asymptotics and so on and so forth. So I just listed one paper, which is probably the first one in the more mathematical literature, at least. So these are two questions. They're obviously a bit related, but they're also somewhat different, okay? So this is well studied. The question of the couplings themselves, not very much has been said about that. Okay, so let's start with some easy and preliminary considerations. We're looking at a sequence pi epsilon, epsilon going to 0. What could happen? Well, firstly, these are all couplings of the same two marginals mu and nu. Those are fixed. Okay, the set of all couplings is weakly compact. That's just a fact. Okay, so that sequence pi epsilon necessarily has accumulation points, at least for weak convergence. Okay, that's for free, and almost for free, sort of for some from Portmanteau's theorem. If you have a limit point of some subsequence, then necessarily that is a solution of the unregularized optimal transport problem. So that's also for free. So then in particular, if you know from somewhere that your optimal transport problem has uniqueness, has only one solution, it immediately follows that all these accumulation points have to coincide. And in fact, pi epsilon would converge to that unique optimal transport. Okay, so in the case where the OT problem has uniqueness, our question is not very interesting. We can ask how fast is the convergence, and that would be interesting, but that's not exactly what I'm looking for here. The question is interesting if there is more than one optimal transport. Okay, so I'm writing here pi OT for the set of all optimal transports. This is for the unregularized problem. Okay, so if that set is not a singleton, then, well, these accumulation points are all in that set. We would hope that they coincide, but it's not clear that they do. And if they do, meaning that the limit exists, you know, we want to kind of know what that limit is. Okay, so it's you know, very intuitive to conjecture that pi epsilon should converge to something. I don't know who was the first person to have that thought, because it's relatively easy to have that thought. I think the first time seeing this stated in some generality is in a paper of Christian Leonard a bit more than 10 years ago. Okay, so if you think from the perspective of unregularized optimal transport, this is like a selection principle. Okay, you have many optimal transports. Is one of them somehow particular? Then you can think, okay, one way to pick one is to introduce entropic regularization, send the epsilon parameter to 0. Hopefully this would pick a very particular optimal transport, which is somehow nice. In my mind, this is very vaguely similar to the vanishing viscosity method in PDE theory, where you have maybe multiple solutions of an equation, then you add epsilon Brownian motion or epsilon Laplacian, send epsilon to 0, and you cover a very particular solution, the so-called viscosity solution. Okay, here, because we define pi epsilon by minimizing relative entropy, there is an intuition that the limit pi 0 should have somehow small relative entropy, because we are doing this relative to the product measure of the marginals. It sort of means that pi 0 should be very spread out, very regular. as a density, it's kind of the opposite of when you look for a Mosh map solution to a problem, because Mosh maps are very concentrated. In some sense, it's the opposite. Okay. So that's the main question. And for that question, there are two regimes that are sort of very different. One regime is easy and one regime is not easy. Okay, so let me start with the easy regime, which I call the finite entropy regime. Okay, so I will assume out of the blue that in that set of optimal transport plans, there is one which has finite relative entropy. Okay, we can assume this. And then see what it means. Okay, so if you have one finite guy, then you can take the relative entropy functional and minimize it over the set of all optimal transports. And from some general nonsense, this will have a unique solution. Okay, basically, if you minimize over a convex closed in total variation set, then there will always be a minimizer for relative entropy, a unique one. So call that guy pi 0. Then this pi 0 is the limit of pi epsilon, and the convergence even holds in total variation. Okay, this is somehow without specifying the details or geometry or anything of the problem. And it just follows by relatively simple, very soft arguments. Okay. What about this assumption? When is it satisfied? When is it not satisfied? So here are probably the two most important examples. One is the setting of discrete optimal transports. So if both marginal measures are just concentrated on finitely many points, then the whole optimal transport problem is just a finite dimensional linear program. We added entropic penalty, and finite dimensional linear programs with entropic penalty have been studied in this paper by Cominetti and San Martin like 30 years ago, and they already show this result in their slightly more general setting in finite dimension. Okay, so this assumption also covers some infinite dimensional settings. So one popular setting in optimal transport is one measure is discrete and the other measure is continuous. That's a so-called semi-discrete optimal transport. For instance, the discrete measure can represent data or samples, and the continuous measure would be some reference or maybe a theoretical distribution that you're converging to. So then it's still true that couplings generally have finite entropy. So we're still in a setting where this theorem applies. If both marginals are continuous, well, you can find examples where it applies. For instance, when the cost is constant, then the solution of this is the product measure itself. But usually it will not be satisfied. So that will be the main focus of this talk. That is the other regime, the infinite entropy regime. Are there questions on this result?
Actually, I have a question, Marcel.
Yeah.
The cost function only enters in the constraint pi OT in the set, no?
Correct. Exactly. Okay. So pi OT, we are only looking at sets at couplings that are optimal transports. So this could be, this dramatically depends, of course, on the cost function, what this is.
Mm-hmm. And if you, talking about the discrete example, if you have mu constant in R2 concentrated in 2 points like this, along a vertical line, and nu is 2 points along a horizontal line, they are, in such a way that any coupling is optimal. So this is one up, one down. This is one left, one right.
Mm-hmm. Yeah, I understand the example.
Optimizer would it be, let's say, for quadratic, or would it be just the obvious thing of doing half-half, left and right?
Yeah, it would. I mean, generally speaking, this relative entropy here, the smallest possible value is 0. So, and that is only attained by the product measure itself. So in any problem and the product measure is always a coupling. So if this actually is an optimal coupling in your OT problem, then this is always the limit we're looking for.
Great, thank you.
In general, we're looking for something that resembles a product, but is constrained to be an optimal transport at the same time. Yes. So maybe that's actually a good thing you highlighted for what's coming up. So here, finding the limit is really a two-stage problem. First stage, solve the optimal transport problem. then minimize the entropy over the resulting set. Yes,
Marcel,
go ahead, Ibrahim.
So I mean, pi OT mu nu, this is a convex set, right?
Yep.
So how far are you from looking at some sort of a projection of product measure to this set here?
In entropy theory, this is called projection.
Okay.
It's not a projection in the metric sense, because KL is not a metric, but it has this intuition, and there is something that resembles the parallelogram identity, which is actually how one can prove, or that's at least one proof, how to show that you actually have minimizers in this case.
Okay, thank you.
So that's a good way to think about it. But it's a projection so usually when you think of projection onto a convex set, you're going to end up at a point on the boundary, right? So this projection is actually not going to be on the boundary. It tends to be more like in the middle of the set. So it's true in this case that the pi zero would have, it would dominate in the sense of absolute continuity all the other optimal transports. So in some sense, I think of pi zero as being a convex combination of all the other optimal transports. Of course, it's not easy to figure out the weights, but it's somehow in the middle of that set.
Oh, that's surprising. Thank you.
Okay, any more questions? It's good to build a bit of intuition for what's coming up. Okay, so this was straightforward. You can solve this problem in a day. Now let's look at the infinite entropy regime. Okay, sounds a bit exotic, but in some sense it's not very exotic at all. At least for mathematicians working in optimal transport, the standard setup is something like this. Your marginal measures have some nice densities with respect to Lebesgue measure in RD, and you have a nice cost function, maybe convex. And then it is observed that in most cases, all optimal transport plans are actually concentrated on lower dimensional sets, at least if the dimension is not 1. Okay, so if optimal transports are concentrated on lower dimensional sets, so it means that they cannot be absolutely continuous with respect to Lebesgue measure, then they can also not be absolutely continuous with respect to mu times nu, if those are absolutely continuous. So it follows that all optimal transports typically have infinite entropy in the continuous setting. Okay, so then we look at the theorem, we try to guess, what could it be? It's a little bit strange because we are trying to minimize relative entropy, but everyone has infinite entropy. So how would I know what that means? At least I don't know what that means. But we may still believe that there's a limit, but somehow this is not clear what. Okay, and to the best of my knowledge, this is a pretty wide open problem. So you can immediately pose the problem in very great generality. What is the limit of pi epsilon? Presumably it exists. I just don't know how to, even showing existence, I really have no idea. Okay, so after having no idea for a sufficiently long time, I thought, okay, let's add a little bit of structure. What is actually an important setting for this problem? So arguably for optimal transport, the most important cost function is the square distance. For square distance, if the marginals are nice, there's a unique solution and we don't have a problem. Okay, so this is not an interesting question in that setting. Then I would argue the second most important cost function in optimal transport is the distance itself. It's the function that gives rise to the one Wasserstein distance, at least in application. And indeed, here we usually have a non-unique solution when the marginals are continuous. So I would say this is probably the canonical example to look at this problem. In fact, if you ask people what is a continuous optimal transport problem with non-unique solution, probably that's the one and only example they would immediately come up with. Okay, so for the rest of the talk, the cost function is the distance on RD, the Euclidean distance. This is also called Monge's problem because in his original treatise 300 years ago, this is actually the cost function that he's looking at. In his case, the dimension d is 2. For us, d will be greater or equal to 2. Probably it's not much more difficult in higher dimension. Okay, so we're going to focus on this problem and ask, what is the limit of pi epsilon? Okay, so we get a little bit of structure from this cost function, and I want to spend a few minutes explaining what that geometric structure is. Okay, so there is a fact which is well known in OT theory. A number of people have worked on it, and namely for the distance cost, all optimal transports transport mass along certain line segments that are called transport rays. Okay, so in particular, if the dimension is more than 1 and the marginals are absolutely continuous with respect to Lebesgue, because all optimal transports are concentrated on some union of rays, it follows they must have infinite relative entropy. So this is really the setting we're interested in, where we don't know how to interpret the minimization of entropy. Dimension 1 is special because the line segment actually has the full dimension in 1 dimension. It's not an easy problem, but more or less, if you remove certain points, namely the mass which is not moved by any optimal transport, if you remove that from the picture, then more or less you reduce to the finite entropy regime. Okay, so there's a nice paper of Di Manino and Duet which does this problem, not from the perspective that I'm looking at it and in my language, but yes, so it's a bit different. It probably doesn't have the core feature that is of interest to us, and they also highlight that their method would probably not extend to any higher dimension. Okay, so let me tell you what how to think about those transport rays. First, very informally in this cartoonish example. So in this cartoon example, the marginals are actually not absolutely continuous. I'm looking at the measure in R2, and my mu measure is concentrated on 3 lines. And the second measure, nu, is also concentrated on 3 lines. It's the same measure, but sort of translated to the right. Okay, so if you're trying to find an optimal transport for the distance cost, well, there are many things that are couplings. For instance, you can send this mass here to down here, and then take this mass and send it up here, and then, I don't know, send the middle to the middle. This is not a great idea in terms of minimizing the cost. Okay, if you want to minimize the cost, you should take this mass and actually send it up here, and the lower part should go to the lower and the middle should go to the middle, because otherwise you're doing this vertical movement, which is costly, but not giving you anything. Okay, so in this picture, there are 3 transport rays. One kind of is here, horizontal straight line. Then there's a second transport ray here. There's a second transport ray here. Okay, so in this concrete example, what the theory says is that anything that's an optimal transport, it should move mass only along those rays. Okay, you can see how there is sort of a mu condition to the transport ray, which is basically just this patch here. Okay, you need to move this patch to this patch along the ray. You are not allowed to like go off the rails and cross over to another ray. Okay, and conversely, in fact, as long as you stick to the ray, you're going to be optimal. Okay, so that's the image I want you to have in mind, even though in general it's quite a bit more complicated object. Okay, so in general, the transport rays they're just the incarnation of C cyclical monotonicity for this particular cost function. Okay, for those of you who know the abstract optimal transport theory. So in general, the OT problem has a dual problem. This is the dual problem. Maximize over functions u plus v less than the cost c, these integrals. And if you do this problem for the particular distance cost, then it simplifies to what is on the right-hand side here. So sup over 1 Lipschitz functions, and then just this integral here. So this is because the c-convex conjugate for the particular cost function here is actually simply the negative of u. And that's how you get here. Anyway, so this dual problem has a solution. Let's call it u. It's called counter-OH potential. Take the counter-OH potential and then consider all maximal segments, so straight line segments in RD with this property here. This is the particular incarnation of the C-cyclically monotone set. Okay, so these are the transport rays by definition. array can be given a direction, which is also the direction of the gradient of u along the ray. And it's a fact that any two rays do not intersect except possibly at the endpoints. Okay, so in this example, you can see the three rays, they don't intersect, not even at the endpoints. In general, this is, of course, quite complicated picture. So I don't know, I imagine some stack of hay. Okay, so there are many straws or maybe chopsticks or something because they have to be really straight. In general, there have to be continuum many, which is why it's a complicated object. And you imagine that you have one measure, mu, which is somewhere concentrated on a subset, maybe here, and another measure, which is maybe concentrated here. If you want to be an optimal transport, you have to follow exactly the straight lines given by those straws in your hay in order to be optimal. Somehow the union of all these straws together, it's a space-filling object. Because it has to carry those measures, it has to be space filling, but each individual straw is a one-dimensional thing. Okay, it's quite horribly complicated. It's best not to think too much about it. So it's a result that a coupling is an optimal transport if and only if it moves mass along rays. So as long as you pick up mass within a ray and deposit it inside the same ray, and you're a coupling, then you're necessarily optimal. Okay, another fact I'm going to use is that we can disintegrate optimal transports over rays. Okay, so basically I can, don't think about it too technically. It basically just means that I can describe an optimal transport by saying what it does to the mass on each ray. Okay, some sort of local description is possible, and I'm going to use that extensively. Okay. So now back to our problem, which is to determine the limit of pi epsilon as epsilon goes to 0. Let's just start with a very simple problem, which actually will be in the finite entropy regime. So here, mu is not absolutely continuous. It's actually a singular measure concentrated on a line, and I'm thinking of that line as being a subset of the plane. Okay, and I'm just going to do the translation. So the other measure is the same thing, but kind of more to the right. So actually, as we discussed when Julio asked his question, if the product measure is an optimal transport, then it has to be our limit that we're looking for. In this case, the product measure of these two things, actually it brings mass only left to right. So here, this is our pi 0 that we're looking for. Okay, so that was easy. Here is the same picture as before with a slightly different question. Okay, we already figured out that if we want to have an optimal transport, we should bring this mass to up here and this mass to up here and so on. And either just by thinking about it straightforwardly or from the transport ray theory, we know that it doesn't really matter how we bring this mass over here, we will always have an optimal transport. So this is actually the so-called book shifting example that probably many of you have seen. So in terms of the transport cost, it doesn't matter whether I take the mass from here and bring it here and take the mass from here and bring it here, or whether, let's say, I take the mass from the middle, put it in the beginning, and take the mass from the end, put it in at the end, or, you can mix it in any way. The transport cost is always the same. The total cost is actually just the distance basically between the midpoints. Okay. Now, in terms of minimizing entropy, they're not all the same. In terms of minimizing entropy, you can think a little bit about it. And what you should be doing is you should be taking the mass from here, sort of the conditional measure that's represented by this one little line that I just encircled, and take the product measure with this other line. Okay, and then do the same thing in the middle and the same thing at the end. Okay, so intuitively, this is also like the most diffuse coupling among those that are optimizers for the transport problem, right? So if you want to stick to each horizontal line, the product is the most diffuse thing you can do. And that would be indeed the solution. We are actually still in the finite entropy regime. If you think a little bit about it, see that here entropy is still finite. Okay, so now I want to sort of move to the continuous limit of this from 3 to 4 to continue many horizontal lines. And this brings me to a problem which is finally interesting. So here mu is the uniform measure on a rectangle in the plane. Nu is also the same thing, but translated to the right. So in this example, there are now continuum many transport rays, but the structure is very, very simple because the rays are just parallel lines going from one side to the other, right? Basically at every height, at every y coordinate or vertical coordinate, there is a horizontal line, and those are my transport rays. So again, in terms of just the optimal transport problem, this problem is trivial. Basically, I have to take the mass which is here and bring it to here for every horizontal line, and it doesn't matter how I do it. Okay. Also, I can sort of do this disintegration. On each line, I have a mass which I call mu bar, and in the picture is obvious that this is just going to be again the Lebesgue measure, the one-dimensional Lebesgue measure on the line, so you don't have to think about too much about what this conditioning really does or means. Okay. So the question is, what is the limit? What is the limit of pi epsilon, some pi zero that hopefully exists? And given what we have done before, I mean, the most spread out thing that you can do is you do exactly what we did before. You take the measure on this ray and couple it in a product measure way with this other measure on the ray, namely, so mu bar times nu bar sort of on every ray. And according to this disintegration story, I can reverse the process. I can just say I do this on each ray, and that will define the global coupling. And that looks like the most spread out one. So that's a very reasonable candidate to be the limit pi zero. Okay. Interestingly, that is reasonable but wrong. That is actually not the limit. And that's where this example starts to be interesting. Okay, so go on. Okay, so in better news, the limit exists and it has a neat description that we can write down. It's just not the description that we just talked about. Okay, as we said, we can describe couplings by saying what they do on each ray. So that's what I'm doing here. I'm picking a ray. All the rays actually look the same in this example. So just pick a representative ray. And on this ray, I couple the conditional marginals. Conditioning here has this overline notation. And the coupling I want to pick on each ray is the solution itself of an EOT problem. Namely, it's the, same thing with respect, entropy with respect to product of the marginals. And there is a cost function C. And this cost function C now kind of came out of nothing. It's minus 1/2 log. Okay, and the epsilon parameter here is just 1. What does this thing look like? First of all, it's not the product measure. The product measure is what you would get if this term were not here and you were just minimizing this. Okay. Conversely, if this were not here and you were just minimizing the cost, then because minus log is a convex function, the solution would be the Brownian map, and the Brownian map here is just a translation map. So that would be the map which takes sort of the leftmost point, brings it to the leftmost point, takes the middle point, bring it to the middle, and takes the right endpoint and bring it to the right point. Just translate everything to the right. So that would be the solution of only this. There are two terms. There's going to be a trade-off between the two. So it's somewhere between the product and the translation. So it's kind of biased. For instance, if I look at a point here and I look at the kernel and I ask, okay, what does the kernel, the transport kernel, do with this mass? So it has to spread it over this line. Because it's an optimal transport, it has to spread it over this line, but it will be not uniform. It will be like biased towards the translation. So it will be like have more mass here than somewhere far away. That's not the exact shape. I'm just giving the vague direction. Okay, so that's the solution of this problem. I think this is already an interesting example because you can see that the solution is completely different from the discrete case. We do not have this two-stage optimization where you can just say, I'm first going to pick an optimal transport and then minimize the entropy. Somehow the two are giving rise to a more complicated expression. So I want to give a tiny bit of intuition for where this term could come from. Really just intuition. So we have to understand the pi epsilon, of course, because ultimately that's what's going to determine the limit of pi epsilon. Let's think that we start from an optimal transport and we try to figure out what pi epsilon could look like. Okay, maybe someone already gave you the limiting optimal transport, some sort of oracle. Okay, so the optimal transport, it picks up mass, say here, it brings it to this line here. It is itself a terrible candidate in the pre-limit problem because it has infinite entropy. Okay, to convert it to something with finite entropy, we have to make it absolutely continuous with respect to this measure nu here. So it means we have to spread the mass also in the vertical direction, not only in the horizontal direction. Okay, and that's where there's going to be a trade-off. By doing that, we save entropy cost, but we pay more transport cost. Why? Because the distance is bigger, right? Originally, we traveled the blue distance, and now we're going to travel the red distance, which is, of course, longer. Okay, so this is going to be more costly here, but we're going to save something on the entropy side. And it turns out that sort of locally at around this transport ray, if I spread things out according to a Gaussian with this variance, then we're, at least back of envelope calculation wise, we're kind of balancing this trade-off. And indeed, so this term is related to the term that shows up here. So this comes from trading off transport and entropy. Okay, I'm running short time, so I'm going to skip this, which is anyway just a very, very sketchy proof. So indeed, this construction that I showed in the picture, it goes into the upper bound at least. This is obviously not going to be a coupling once you just spread it out, but you can sort of do a lot of cutting and pasting because this is a fairly explicit example. You can sort of really construct a coupling from that idea, and that goes into the proof at least. Okay. So the example was very special. It doesn't really capture the whole truth. One thing that's very special in that example is that the rays are parallel. Okay, so let's have a second example where the rays are not parallel. So we call this the fan example. It's like a silk fan, an ancient fan in China or Japan. Okay, so these green bits are the two marginals. They're uniform. So you should think that there is some center of the circle very much to the left here. Okay, so these are sections of annuli, okay, concentric annuli. So there's a measure here, there's a measure here. You want to transport them optimally according to the distance cost. It's quite intuitive that you should move mass only in radial direction. Okay, so here again, it's very nice because we know exactly what the transport rays are. They are basically all the radial directions. Okay, everything is super smooth and explicit. They are not parallel anymore, so that's why this example is a little different from the previous one. In radial coordinates, it looks the same, but it's not really the same in Euclidean coordinates. Okay, so now we do this similar trade-off picture. It is a similar picture. You do the details, and it works similar, but the variance we have to pick is actually a different one. Okay, the variance we have to pick depends on the true transport rays. There's this additional term here, which uses basically the distance of those points to the center of the circle. And that is a way of encoding the angle between the two transport rays. Okay. More generally, a function that is always good to look at in optimal transport is this detachment here. So it's a difference between the cost function and the sum of the potentials. It's a quantity that is zero on the transport ray, but becomes non-zero when we move away from the ray. It somehow says how fast the potentials are detaching. And it turns out, I think this is a new result, that if you move in a direction orthogonal to the ray, there is a quadratic detachment, approximately quadratic detachment. Okay, so there are such results for quadratic cost and certain other costs. Clearly, there cannot be a general quadratic detachment estimate for distance cost, because that would tell us essentially that the solution is unique, and it's not. But it turns out that at least at the right points in orthogonal directions, there is a quadratic detachment. And this number here, it goes into the variance that we need to pick when we diffuse out the measure. So because E has U, and the gradient of U is the direction of the transport ray, this is the quadratic coefficient, so it basically has the second derivative. You see that it captures the derivative or the change in direction between the transport rays. Okay, so different proof, slightly different construction, yet when you characterize the limit is the same as before in terms of its intrinsic local characterization. So the theorem we wrote here actually applies to the fan example, that we wrote here. This is true in the fan example as well. Okay, so at this stage, you can take a leap of faith. We go back to fairly general marginals. The situation looks, unfortunately, much more complicated. Usually this is a very non-smooth object, so it's a lot of technical work, but we kind of hope that the theorem is the same. Okay, so the setup we're using is inspired by a paper of Evans and Gangbo. We're using Lipschitz marginal densities, compact supports. For the moment, we take them to be non-intersecting, which makes some technical things a bit easier. We actually separate them by a hyperplane because this gives us a nice parametrization of the transport rays. Maybe we can remove some of those conditions towards the end, but the tentative theorem for now is that pi epsilon does converge. It does converge to a coupling pi 0, which has the same sort of conditional or local description as in the very simple example that I started with. So the overarching idea somehow is that this whole problem really localizes around each transport ray, and that, yeah, for that reason, you don't have to like capture the whole geometry of that, thing here, but really it's a local matter. Of course, when you try to prove that it localizes, you have to actually deal with the global matter. So that's why things are quite difficult. And in contrast to the examples, the lines here, even the direction is not very regular. It's not so easy to do any explicit constructions as before. Okay, but because Chen Yang is a genius, we hope that there would be such a result within the next year or so. All right, so time to conclude, just slightly over time. So we saw that in the discrete case, or more generally in the finite entropy regime, finding the limit of the entropic optimal transport pi epsilon is like a two-stage thing. First, we minimize the transport cost. So then we have the set of all optimal transport couplings. Then within that set, we minimize relative entropy as a unique solution that will be the limit of pi epsilon. Then we looked at the distance cost problem, and we saw that at least if the dimension is bigger than 1, the whole thing is really fundamentally different. There still is a limit. I believe it's the first result in this direction. And we see here that there is really a trade-off between the transport cost and the relative entropy that enters in determining the limit. Okay, and maybe surprisingly, the solution still seems to admit some sort of very neat, nice description. Okay, so a priori, when we went back to the abstract question, I think a lot of ideas have been around over the years. For instance, maybe there is some other notion of entropy, and there are many notions of entropy in this world. Maybe there's some other notion that remains finite, and you can use that and just pick the minimizer for that thing, and it will give you the result in a similar fashion as in the finite entropy regime. After seeing this analysis, I'm a bit more skeptical that there could be such a very nice soft approach, because it really seems that the limit is picking up a lot of details of the problem. But yeah, obviously the last word is not spoken on that. I would be very interested to see also solutions of other related problems. But for the moment, this is what we have. Thank you.
Thank you very much, Marcel, for the beautiful talk. I see there are some questions in the chat. Maybe you can give a look.
There's a question whether the result on optimal transport is specific for the distance cost. The answer is yes, it is very specific to the distance cost. The correct generalization of this is that there is a set which is called the C-cyclically monotone set, and so the shape of that set would very much depend on the cost function. But it would be true that a transport is optimal if and only if it is concentrated on that set. So that's the general result that follows from duality theory and could be found, for instance, in Villani's book. Can dimension d greater than 1 in Mosh problem be any real number? No, it is an integer. I have never thought about non-integer dimension. Sorry. Someone, okay, it says raised hands, but I don't know about, I think feel free to open the mic and just ask.
Yes, maybe Leona, I saw you raise the hand first.
Yeah, thank you. Thank you, Marcel, for the very nice talk. Question, you choose as a reference measure the tensor product of your marginals. How sensitive is your result to that particular choice? I guess very sensitive, right?
Yeah. You're guessing what, sorry?
So the reference measure that you use for the entropy term, the epsilon entropy penalization,
yes,
you choose the tensor product of your two marginals. What if I chose some other measure? I guess your result strongly leverages this particular choice, right?
Yes and no. So
I mean, the range structure, of course, has nothing to do with that. That's the...
Yeah, so it turns out because of the very, very specific algebra of the relative entropy function, that when we look at the EOT problem, this thing here, if I change this, mu and nu here, but I keep them to determine the marginals, the optimal coupling is actually the exact same coupling as before. So the pi epsilon does not change if I change this into some other measures. The moment it is not a product measure, it can be anything. Okay, in fact, this problem can be rewritten, or the solution is also the minimizer of entropy without transport, okay, just entropy with respect to e to the minus c over epsilon Gibbs kernel, mu times nu. Okay, so this is a new measure R. So you can see that from this, that by changing the measure R, you can solve the problem for any cost. So this would completely change the structure if it's no longer a product measure. But as long as it's a product measure, and so basically what other measure you want to choose, maybe you want to choose Lebesgue measure, right? Lebesgue measure is actually a product measure. So if you do that, as long as it's in the same, absolute continuity equivalence class as the mu nu, which it would be in this case, it would actually not change the solution. This is very, very specific to entropic penalization. It's not true for other penalizations, but here it is true.
Mm-hmm. So just the support of the reference measure actually matters, right? I mean, in some sense.
Yeah, modular details.
Yeah. Yes. I see. Thank you.
Yes, I think someone else had raised their hand. Are there any more questions?
Thanks, Julio. Yeah, really nice talk. Thank you for the talk, Marcel. The question I have is, are you able to describe in broad terms what pi zero looks like in the special case where mu and nu are both uniform measures on convex bodies in R to the D?
No.
Okay. Do you expect some sort of broad analog of this log result you have in the rectangle case?
Oh, sorry. So what was sort of the main takeaway is that result is actually probably true in even greater generality. So not just for the example you just gave. So the local description would actually be the exact same. Sorry, this is for 2 dimension, and if the dimension is not 2, there is an exponent somewhere. But apart from that detail, the theorem would extend to the general case. So basically, what the rays look like would, of course, depend quite a lot on the given marginals.
Yeah.
But then I can describe the coupling by saying what it does on each ray. And in that sense, the result would be the same. That's
so
our belief at the moment, and it's proved up to significant technical details.
Okay. Thank you very much.
I have one question if we have time.
Yep.
What happens, I mean, so as you said, I mean, when you regularize with entropy, it's essentially you change the cost. What if you directly change the cost? For example, instead of taking the L1 norm, you take LP norm P and send P to infinity. Do you expect anything there that these maps converge to something? Because if you take LP norm for cost, then there is a unique optimizer. So, and then
yes. So you're interested in sending P to infinity?
P to 1.
Oh.
So that I converge to the W1.
Yes, and you're doing this with entropic regularization or without entropic regularization?
Because pre-limit, I have a
yeah. So this is a study problem. So if this is done, if you do this in the right way, which is not completely straightforward, but then you would pick a solution of the distance cost problem, but this would be sort of the opposite of what we are trying to do. So what you would be picking then, and so this was studied so the classical problem is try to find a Morse map solution of the Morse problem. So the distance cost problem, try to find an optimal coupling, which is given by a map. Okay, so this was very heavily studied by including all those papers that I listed here. Like that's what they're really going after, the ones on the top of this slide, and various more. And so one of the ideas there was, okay, take P strictly bigger than 1. I have a Morse map, send P to 0, hopefully it will converge to a Morse map. And that would be a way of constructing the solution. And that's one of the things that has been done, even though it's not exactly here. Yeah.
You're finding essential
so that would pick a very concentrated solution. There's more than one Morse map because, so essentially you want to pick a Morse map on every array, like a one-dimensional thing that should be easy, and then kind of glue them together to get a global Morse map. And that essentially works, but turns out that there are pitfalls and it's a bit difficult. That's why there's such an extensive literature around that problem.
Thank you.
Yeah, maybe we'll have time for one last quick question.
Can I ask a question, actually? So
yep.
In your very first result, when you have, in the kind of the easy case, you had convergence and total variation. And I didn't mention,
yep.
I missed what kind of mode of convergence you had in your other results. Maybe you mentioned it. I suppose you can't expect it to have variation.
Here it's all weak convergence because the moment where the limiting coupling has a smaller support, in fact, even a null set as a support, they have to be mutually singular. So there's no way that there can be total variation convergence. And we're using the weak convergence. Yes, which, okay, because here things are kind of bounded and nice. It's the same as Wasserstein convergence.
Right, okay. Yeah, I guess somehow would you even expect a converse to that? Like if you do have convergence or total variation, then you have to kind of be in the easy case.
Yes. Yes. So in fact, yeah, there's something that sort of you're in this setting, if and only if you have TV convergence at a certain linear rate or better. That's a result, I think, is in my lecture notes.
Okay, thanks.
Okay. Well, thank you very much, Marcel, again for this wonderful talk.
Thank you. Thank you again.
Thank you. So, are you around, Stephan?
Yes, I'm around. So I can share my slides.
Please.
Okay.
So I think we can start right away, just in time. That's perfect. I'm very happy to introduce Stephan Eckstein, who, yes, presently is at ETH Zurich, but as of Wednesday next week, he will be in Tübingen, Germany. Yes, please, the floor is yours, Stephan.
Yeah, thanks a lot, Julio. Yeah, thanks to all the organizers for giving me the chance to talk here. So I'm talking about the very recent work, also in this direction of entropic optimal transport, as in the talk by Marcel. So for me, the focus is more really on just the entropic transport. So for Marcel, of course, entropic transport was a kind of approximation of the initial optimal transport problem. And I'm really interested in just the entropic regularized problem. Particularly, I will look at probably the most famous algorithm to compute this kind of entropic problem, which is called Sinkhorn's algorithm. And I'm going to be interested in the exponential convergence of this algorithm. And particularly, I will look at a certain method to prove the convergence of this algorithm, which is based on Hilbert's metric. And let's say a key novelty of what I'm doing in this regard is that I make this applicable even in unbounded settings. So very broadly, the goal of the talk is to show you that Hilbert's metric is, let's say, a powerful tool in the study of something like entropic optimal transport and Sinkhorn's algorithm. And particularly, as mentioned, the novelty is that this can be applied in unbounded settings. So the outline is broadly as follows. So first, I also want to shortly recap this intro to entropic optimal transport and more particularly to Sinkhorn's algorithm. And then I will introduce to you what Hilbert's metric is, and then also motivate and define this new version of Hilbert's metric, which should be suitable for these unbounded probabilistic settings. And then finally, we'll go back to this motivation by Sinkhorn's algorithm and use this version of Hilbert's metric to prove exponential convergence in such unbounded settings. Okay, so the setting looks very similar to the talk by Marcel. So again, we have two marginals, mu and nu. Here we just assume they're in the same space X, so they are Borel probability measure on a Polish space X. The cost is again denoted by C, so it's a non-negative cost. It's measurable and integrable with respect to the product measure of the marginals. And we have exactly the same objective for the entropic optimal transport problem. So we minimize over all couplings between mu and nu, this integrated cost of transport, plus this entropic regularization term. So here the main difference to the previous talk is that for us, this epsilon is just a fixed constant. We will not vary this throughout the talk. And in fact, we're not going to look very much at this kind of problem. The key thing that we're interested in is really trying to find the optimizer of this entropic optimal transport problem for a finite epsilon. And the way we want to do this is via Sinkhorn's algorithm. So Sinkhorn's algorithm can be described with the Schrödinger equations. And so this the unique optimizer of this entropic optimal transport problem can be described by its density with respect to the product measure of the marginals. And this looks as follows. So the density is given as the product of three functions. So one function here is just the exponential of minus the cost divided by epsilon. So this term is, of course, easy. This is just fixed depending on the problem. The more difficult terms are these two here. So G1 star of X times G2 star of Y. So in fact, these two functions are determined as solutions to the Schrödinger equations. So G1 star is the fraction of 1 divided this integral of G2 star times the same exponential term, which also occurs in the density, and then integrated with respect to nu. And G2 star has to satisfy the same kind of equation. Just here, G2 is replaced by G1, and we integrate with respect to mu instead of nu. And for the sake of going towards Sinkhorn's algorithm, we consider these fractions or the Schrödinger equations to be defined by two operators, T nu and T mu. So here, we consider this fraction here as the output of an operator T nu evaluated at this function G2 star. So here, this fraction is seen as the output of this operator T nu evaluated at this function G2 star. And here at the bottom, similarly, this fraction is considered as the operator T mu evaluated at the function G1 star. And yeah, just introducing this notation, we can write the Schrödinger equations more simply as just G1 star is equal to T nu of G2 star, and G2 star is equal to T nu of G1 star. So this is just a set of two equations. And what now Synchron's algorithm is doing is just trying to find a solution of these equations by iteratively solving one of the two equations. So it's very simple. We initialize the functions g1 and g2 somehow, for instance, just to the constant 1 function. And then iteratively we define one of the functions, so for instance g1 of n, as the operator t nu evaluated at g2 of n minus 1. So then the pair of these two functions satisfies this first equation. And then we define g2 of n as the operator t mu of g1 of n. So then these two functions satisfy basically the second equation. So we iteratively solve one of these two equations so that in the limit, hopefully these two functions should actually satisfy the set of equations. So the goal is really that this function g1 of g1n should approximate g1 star, and the function g2n should approximate g2 star. And this kind of convergence is really, let's say, the key topic of this talk. Let me give you a bit of background on the study of this algorithm, on Synchron's algorithm. So because there's really, let's say, a lot of literature, I want to really restrict to just papers dealing with the exponential convergence of Synchron's algorithm. So this is basically the study of the fastest possible rate of convergence which is available for this algorithm. So in the early works, people mainly dealt with discrete marginals, so marginal distributions which are only supported on finitely many points. And in this regard, Synchron's algorithm was also called matrix scaling. And there already in 1981, it was shown that by Franklin and Lorentz that this algorithm converges with exponential rate, and they used the method also based on a certain version of Hilbert's metric. Then later on, this result was generalized to allow for more general marginals. But here still, so this was generalized by Chen and co-authors and Carlier. But here still the fundamental limitation that the cost needs to be bounded remained. So this, again, as in Marcel's talk, this would exclude the, let's say, interesting cases like quadratic cost function or the distance cost function. So yeah, this was still quite limited, let's say. And really the first result which proves the exponential convergence of Synchron's algorithm even in an unbounded setting was given earlier this year in a paper by Conforti and co-authors. So they're basically studying a setting where both the marginals and the cost functions satisfy certain smoothness conditions. And then they can use a certain approach based on stochastic control. So they really leverage the fact that the problem has some nice smoothness properties in this setting. Now what this paper or this talk, what I want to show you is that we can actually obtain exponential convergence of Synchron's algorithm just with suitable tail conditions on the marginals or correspondingly suitably bounded growth of the cost function. So in a sense, the marginals of the tails of the marginals need to be sufficiently light compared to the order of growth of the cost function. And so on the one hand, I think this is a very interesting result regarding the study of Synchron's algorithm. But on the other hand, I also think that in terms of the methodology, this is based on a version of Hilbert's metric. But in contrast to these earlier works, which also built on Hilbert's metric, here a new version is used. And while earlier works used this, what I call the L-infinity version, which I will also show in a few slides, here this L-infinity version was really restricted in its applicability to unbounded settings. And here this new version is so to say tailored to be also applicable to these unbounded probabilistic settings. Okay, so next I want to first talk to you about why we would even be interested in something like Hilbert's metric. So what is the goal of using something like Hilbert's metric? So the basic goal is to obtain contraction properties of these operators T nu and T mu, which define a Synchron's algorithm under some metric T. Let's say if we had that, if we knew that both of these operators were contractions with contraction coefficients kappa, then it would be very easy to obtain exponential convergence. Yeah, we could just evaluate here the distance between G1 star and G1 of n. We plug in here this defining equation with the operator T nu. We use contractivity, and then we repeat the argument for the other operator T mu. And then we see that here the distance for this index n is bounded by kappa squared times the distance for the same distance, but the index n minus 1. And then, of course, iterating this argument directly shows exponential convergence. So the goal is really to find such a metric such that these operators are contractions, and then it's very simple. And Hilbert's metric, broadly speaking, denotes a family of projective metrics, which are in a way tailored to yield contraction properties of various operators. This is mainly a consequence of a famous theorem by Birkhoff called Birkhoff's contraction theorem. Okay, so let's now talk about really what Hilbert's metric really is. So again, first, broadly speaking, Hilbert's metric is a family of different distances, and each version of Hilbert's metric on some space Y corresponds to a certain cone in this space Y. So for us, spaces of functions are of interest. So for instance, we work with L2 spaces for each of our marginals. So for instance, Y could be the L2 space under mu. And then let's first recall what this baseline version of Hilbert's metric is. So this is what I call the L infinity version of Hilbert's metric. And again, this is probably at least from my point of view, the most frequently studied version of Hilbert's metric. And this is also employed in all bounded settings for the study of Synchron's algorithm. So here the cone C is simply the set of all non-negative functions. So all these properties are always understood mu almost surely. So here the cone C is simply the set of all functions which are larger or equal than 0. And of course, it's pretty clear that this is a cone. So if you scale a function in the set C by a positive scalar, then it's still in the set C. And then the corresponding version of Hilbert's metric can be given here as follows. So this is defined as, so to compute this, you take both of these fractions. So for two functions, g and g tilde, you look at both fractions, g divided by g tilde and g tilde divided by g. Then for both of these fractions, you look at the largest value, so the infinity norm. Remember, these are positive functions, so these fractions are also positive. So you look at the largest value, and then you take the logarithms and sum these. And here again, I should emphasize that this infinity norm is understood as the mu essential supremum. So this might now look perhaps at first sight a bit unfamiliar to some of you. And I would just want to emphasize that this definition here really defines a projective metric. So it basically satisfies all properties of a metric. The only thing that's missing is that if the metric between two functions, g and g tilde, is 0, this does not necessarily imply that g equals g tilde, but it only implies that g tilde is equal to some positive scalar multiplied by g. So this is how the term projective distance comes from, because the magnitude of the functions is not important, and only, let's say, the structure of the functions is important. So as long as two functions have like the same shape but different magnitudes, the distance will still be 0. And let's say what this baseline version of Hilbert's metric, what I believe the main limitation of this metric is that as soon as either of these two fractions, g divided by g tilde or g tilde divided by g, are unbounded, then this metric is immediately meaningless because it just evaluates to infinity. So of course, this is easily seen to be true. So here, just if you plug in some fraction which is unbounded, then of course one of the two terms would be infinite. And I just want to emphasize that if you're working in unbounded settings, even if you have just something like two quite well-behaved functions, for instance, if G has quadratic growth and G tilde has linear growth, then even in such a, let's say, relatively well-behaved setting, it would still be the case, of course, that this fraction somehow goes to infinity, and then this version of Hilbert's metric would already be meaningless. And the motivation for this work is really to find a version of Hilbert's metric which is meaningful in these unbounded probabilistic settings. So the main idea to achieve this is the following. So we first observe a trivial reformulation of this cone of all non-negative functions. So we emphasize that this cone of all non-negative functions can equivalently be written as the set of all functions G, such that this integral f times G d mu is non-negative for all non-negative test functions. So it's clear that any non-negative function G satisfies this inequality, and conversely, if a function satisfies these inequalities for all test functions f, for all non-negative test functions, then G also needs to be non-negative. So it's really just a fancy way of writing the set of all non-negative functions. Analogously, this Hilbert metric between G and G tilde can also be written, instead of this infinity norm of the fraction between G and G tilde, it can be written here as the supremum over all the test functions. And here, instead of the infinity norm of the fraction, we can write this fraction of the integrals fg d mu divided by fg tilde d mu. So again, this is just a way of rewriting this cone C and the corresponding Hilbert metric. And the reason this is kind of intuitively interesting is because we see here that basically the definition depends on some set of test functions. So we can also replace this by different test functions. And that is basically the principal idea of this work, is that instead of the set of all non-negative test functions, we work with different sets of test functions f. So then we define this cone C or CF here as the set of functions G, where really, again, we require this kind of inequality, but instead of all non-negative functions, we require this inequality only for all test functions f in the set f. And then similarly, we want that the corresponding metric is here just such a supremum over these test functions. And just to emphasize intuitively why this could help us, we want to avoid that this distance is infinite in too many cases. So by, of course, restricting here the set of functions which are used in the supremum, making the set in the supremum smaller, we, of course, make the corresponding metric smaller as well. So using smaller sets of test functions can help us make this distance meaningful for a larger set of functions G and G tilde. Now, of course, the question is, how do we choose the set F? I want to do this first at a simple example. So let's look at a simple case where the space X is simply the positive real line. And the measure mu is maybe something very light-tailed, like the distribution of the absolute value of X, where X is just standard normal. And then here I plotted two functions, G, which is just something linearly growing, and G tilde, which is something which stays roughly constant. And then, of course, just for the computation of this baseline version of Hilbert's metric, these kind of fractions occur. And of course, if we take these test functions f as these kind of kink functions, then we see if this function f goes further and further out in the tails, then of course this integral here, f times g, will grow larger and larger, whereas this integral f g tilde will stay roughly the same size. So this shows that here, this supremum, and therefore this Hilbert metric between G and G tilde would be infinite. And this is kind of what we want to avoid. So this means what we want to avoid is that these test functions can go arbitrarily far out into the tails. And the way we do this, so the question is how to choose the set F so that this is not possible to put this mass arbitrarily far into the tail. And the idea is that, well, we simply restrict the mass that f can put in the tail. So if f is some test function, some feasible test function, then we want to require that the integral of f in the tails, so outside of the interval 0 to r, so only on the interval r to infinity, that this interval over f divided by the interval of f on the whole positive real line, this has to be bounded by some predefined factor alpha of r. So depending on here, where this integral starts. So I visualize this here. So this orange curve is just what we predefine this bound. So here near the origin, we don't care too much, but then once we get into the tails, we really want to restrict how much mass the function f can put into the tail. Here I again plotted such a function f, and correspondingly this red line here shows the corresponding fraction for this function f, independence on the radius r. And then once we move this function f further into the tails, of course at some point this fraction of the mass f, this red line will be above the orange line, so f will no longer be a feasible test function. And now, of course, this is good in the way that this kind of behavior, which we try to avoid in this previous example, that the distance between g and g tilde is infinite, this is avoided. But I also want to mention that we still have to pay attention that such functions, such test functions, can still put some attention into the tail. So we don't want to restrict the applicability to some tail behavior, so it should still see the tail behavior somehow. And this is still possible with this definition, because once the test function puts some mass here near the origin, then it actually can still attend also to this mass in the tails. It just cannot do so exclusively, okay? It has to put some emphasis also into this space near the origin. Okay, so I hope this was intuitively, let's say, a little bit clear. So this is basically the whole motivation for this set of test functions and let's say the general definition of this Hilbert's metric, which we'll use. And yeah, this really now gives us already the general definition. So we fix in our Polish space, we fix some x0, which we use as the origin, so to say. And then instead of these intervals from 0 to r, we work with balls around this origin x0 of radius r. We work with some decreasing function alpha, and the complement of these balls is denoted by BRC. And then, as in the previous example, really the definition is that, or the prior example motivates the definition that we work with the test functions, which are non-negative, and the tails, so the mass that the function f puts here outside of this ball of radius r, has to be restricted, again, in a fractional sense compared to the whole mass of f, by such the predefined function alpha. And then the cone is defined as previously, just as all the functions g, such that this integral is non-negative for all test functions f. Now, let's say I would like to work with this definition. It's just that this definition doesn't quite work out. So and there's a slight problem, because if we're working in unbounded settings, and later on we want to have some kind of uniform estimates for these functions g in this cone, and with this definition, the problem is that the tails of g, especially the positive tails of g, are completely unconstrained. So we do not have any kind of control on the positive tails of g. And this would in particular prevent us from obtaining strict contractions later on. So the solution here is slightly technical, but also a little bit intuitive. So we have to allow the test functions here in the set f to be slightly negative, to allow also for negative values in the tails. And these, similarly, how the positive values of f constrain the negative values of g, the negative values of f will constrain the positive values of g, okay? And in this sense, we can also control the positive tails of g. So again, I don't want to go into too much detail here, but here just the formal definition. So we only require now the function f to be non-negative on this ball of radius m, where m is some predefined number. And then outside of this unit ball, the function f can really be either positive or negative. But again, in any case, both, let's say, the positive mass of this function f and the negative mass of this function f are constrained in the same way as we motivated. Okay? And this is really now the definition which works out for us, and yeah, which was basically now the hard part of this talk, to end up with this definition, and now we can, let's say, reap the benefits. And first, what I want to show you is that this now really, let's say, does what it should do. So first of all, what we define here is really a cone. So more precisely, this is actually a closed convex set. It satisfies this cone property, so positive scaling remains the same set. And it's also a pointed cone. So the cone intersected with the negative of the cone is only the zero function. And also this formula, which we motivated all earlier intuitively, is really the corresponding Hilbert metric. So of course, I haven't told you precisely what the general definition for Hilbert's metric looks like, but here the general definition of Hilbert's metric really reduces to this formula which we wanted, that we have this kind of supremum over the test function of these fractions of the integrals. And then also, I mean, we defined now some kind of a metric. So it's always good to know that it's not some kind of pure abstract nonsense, that it doesn't have any kind of relation to known quantities. So one kind of good sanity check is that we can bound really frequently used distances with this metric. So for instance, we can bound the distance in the L1 norm for two functions g and g tilde using this Hilbert metric between g and g tilde. And the most important thing here is that, of course, here on the left-hand side, this term depends on the projective metric, whereas the left-hand side is really sensitive to the scales of this function. So here it's important that the function that this is true for are normalized to have L1 norm equals to 1. But yeah, this should just emphasize shortly that this is really a sensible metric which roughly does what it should. And now, let's say, coming back to the real motivation of the talk, I want to show how we can use this metric to obtain exponential convergence of synchronous algorithms. So we want to show that the operators T mu and T nu are contraction with respect to such suitably specified versions of Hilbert's metric. To this end, we'll actually decompose these operators. So without loss of generality, we'll only look at T mu and not T nu. And we'll decompose T mu as the concatenation of an operator S and an operator LK mu. So the operator LK mu is simply a kernel integral operator. So it's a standard kernel integral operator. LK mu of G is the integral of K times the function G integrated with respect to mu. So this term basically describes what was written in the denominator of this definition with the Schrödinger equations. And hereby this kernel K is given by this exponential term depending on the cost and the regularization parameter. This operator S, on the other hand, is simply the inversion operator. So S evaluated at a positive function G is simply 1 divided by this function G. So let us first look at this operator, this kernel integral operator. So again, so this kernel integral operator, this is what this operator LK mu is. And the baseline result for such kernel integral operators, the baseline result is given by Birkhoff in 1957. So this states that kernel integral operators are contractions with respect to the L infinity version of Hilbert's metric if K is bounded away from 0. So we really need that the infimum over all points in the space of k of xy has to be strictly bigger than 0. But this, of course, in our case, this kernel k was defined through the cost function of our entropic optimal transport problem. So this condition precisely means that it restricts the applicability to bounded settings. So we need that the cost function is almost surely bounded. Well, in this formulation here, it has to be bounded, but of course, all these properties should mostly be regarded as having to hold almost surely in some suitable sense. So what we now can prove for this new version of Hilbert's metric is a generalization of this result. So what we require is just that the limit for the radius r to infinity of the mass that mu puts into the tail divided by the infimum over all values in the ball of radius r of k squared of x of y, this has to be 0. And I just want to emphasize that this is really a weaker condition than this condition that k is uniformly bounded from below. Because of course, if k is uniformly bounded from below, then this term here in the denominator is strictly positive, so it's bounded away from 0 as well. Whereas this term here, of course, converges to 0. So the general condition should be seen that this decay of the mass which mu puts into the tails, which mu puts onto the set outside of the ball of radius r, this mass has to go to 0 faster than the values of the kernel k inside of this ball of radius r. So it's really, let's say, a balancing of this tail decay compared to the growth of the cost c. So if we have this condition, then really the same kind of result holds. So then we get that there exists such a cone of the form which we motivated, such that this kernel integral operator is really a contraction. Okay, so I shortly just want to say that, of course, for Synchron's algorithm, we need to allow for different measures mu and mu. So in the previous theorem, we just looked at one measure mu, but actually this kernel integral operator kind of connects these two marginals mu and mu. So we need actually a slightly stronger result regarding these kernel integral operators. And here to this end, I just want to introduce this notation that this set f, if it's defined as previously, is just written as f, mu, and alpha, or analogously, we write it with the indices nu and alpha tilde if some other measure or some other growth function is used. And then I just want to say that under, again, similar conditions as in the previous theorem, we can again get some kind of contraction property. The only difference is that here now on the left-hand side, we have this cone which depends on mu and alpha. And here on the left-hand side, we have the cone which depends now on this different marginal mu and some possibly other growth function alpha tilde, which controls the tails of these test functions. So it's really just a more general version for this contraction theorem. And in fact, the theorem on the previous slide simply follows by choosing mu equal to nu and alpha equal to alpha tilde suitably chosen. So this just should emphasize that we can really nicely deal with kernel integral operators as long as we juggle the growths in the problem suitably. Next, I shortly want to talk about this inversion operator. And in fact, this is very nice. We can very nicely deal with this. And first, I want to show you, just to build a bit of intuition, how we can deal with this inversion operator for this baseline L infinity version of Hilbert's metric. And in this case, it's actually clear that this operator S is an isometry. So this Hilbert metric between G and G tilde is defined as shown here. And it is clear that, of course, this fraction G divided by G tilde is just the same as 1 over G tilde divided by 1 over G. And with this simple computation, one immediately sees that this is the same as the metric of 1 over G and 1 over G tilde. So in this sense, this inversion operator is really an isometry with respect to this L infinity version of Hilbert's metric. And in fact, what I just recently recognized actually when preparing this talk is that this isometry property is actually a particular version of a more general isometry property for this baseline version of Hilbert's metric. So this more general property is that for some strictly positive function h, we actually have that the distance between g and g tilde is equal to the distance between g times h and g tilde times h. And again, this is completely trivial. This function h simply cancels out in both of these fractions. So it's very simple, but what I haven't realized before I prepared this talk is that actually this property is a generalization of this property by using the function h as 1 over g times g tilde. So of course, in this case, then here, this term reduces to 1 over g tilde, and this term reduces to 1 over g. And the nice thing is that actually this isometry property can be generalized to our new version of Hilbert's metric. This is generalized as follows. So if h is some positive function, and now of suitably bounded growth, let's say, then again, I'm a bit imprecise here, but for suitably chosen then alpha tilde, we actually don't quite get this equality as here, but we at least get an inequality. So the Hilbert metric with this growth alpha of g times h and g tilde times h is bounded by a Hilbert metric between g and g tilde, but here we have slightly different order of growth alpha tilde compared to alpha. And the intuition is basically that this function h needs to be absorbed into this new set of test functions. So this new set of test functions here on the left-hand side, this must contain all functions f times h, where f is a test function here on the left-hand side. Yeah, so simply this function h here is absorbed into the set of test functions. And then, of course, with the same reasoning as here, this reasoning also allows us to control this inversion operator. We just, let's say, lose a little bit in the growth here of the test functions. But now we can actually put things together to obtain convergence of Synchron's algorithm. So again, I'm a bit imprecise here with respect to the conditions, but basically the computation is as follows. So we start, let's say, with some Hilbert metric between G2 star and G2n. We plug in the definition with these operators. And then at first we deal with this inversion operator S. So we get this inequality as derived on the previous slide. And the only thing which we have to take care of is that here actually this growth alpha changes to some different growth alpha tilde. But now the nice thing is that we had this general result for the kernel integral operators. So where we can get back from this growth alpha tilde to, again, the level of growth which we started with, this level alpha. And and then just repeating these steps with new and new reversed actually gets us this kind of contraction property for the algorithm as we want. So I just want to emphasize that basically this operator S, this inversion operator there, we lose a little bit, but this contraction, this integral operator, again, contracts things back to the level which we need. So here we win something and here we lose a little bit. And then just to summarize here the result, we basically just need sufficient growth of the cost function. So the cost function C needs to have, let's say, growth of order P. And we need a little bit of slack compared to this rate of growth of the cost for the decay of the tails of the marginals. So these marginals need to have exponential tails of order P plus delta for some small delta bigger than 0. And if we have these kind of growth conditions, then this argument sketched on the previous slides really goes through, and Synchron's algorithm converges with exponential rate. And I just want to emphasize again that it's nice and all to have this convergence with respect to this new version of Hilbert's metric. But of course, we would actually like to have this kind of convergence also in more frequently used metrics. And here I will want just to shortly show you a corollary for the total variation norm. So of course, using these iterations of Hilbert's Synchron's algorithm, we can also define a primal iteration of Synchron's algorithm, just in the same way as the optimizer of the EOT problem was defined through G1 star and G2 star. If we define this pi n with this density, then under the same assumptions as in the previous theorem, we can actually show that we also have this exponential convergence of these primal iterations with respect to the total variation norm. So, and the idea is simply just what I shown you earlier, that this version of Hilbert's metric is enough to control the L1 norm between different functions. And of course, total variation norm is basically just L1 norm between densities. So in this way, this convergence in the Hilbert metric also gives us convergence in total variation norm. Okay, and that's already what I wanted to talk about. So in conclusion, I wanted to introduce this version of Hilbert's metric, which is suitable for unbounded functions. So as shown, this results from a relaxation of the cone of all non-negative functions. And this is made rigorous through test functions, which are somehow suitably restricted in the tails. Now, Synchron's iterations are then shown to be contractions with respect to suitable specifications of this version of Hilbert's metric. And finally, this is not just some detached result from previous work, but we can actually show that we can control differences in L1 norm, which among others shows that these primal iterations of Synchron's algorithm also converge in total variation norm. So yeah, preprint is on arXiv, and yeah, thanks a lot for your attention.
Thank you very much, Stephan, for your very nice talk.
Yeah, thanks.
Are there any questions from the audience? There's a question in the chat, Stephan.
Ah, okay. Yes, a good question. It's actually, so in these cases that I presented, so the question is whether this new version of Hilbert's metric actually is a Hilbert metric. So if it's non-zero for different points, and how does it depend on the test functions? Yeah, so first of all, it is in a sense a Hilbert metric. So in the way that, so this set CF, which we define, maybe I'll go back to that. This really is a cone, and basically any cone gives us really a Hilbert metric. Of course, Hilbert metric is not really a metric, so it's not. It's just a projective metric, but yeah, maybe I'm missing also the precise question. It's so the question is whether it is non-zero for different points. Yeah, I mean, again, it's non-zero for different points. I mean, it kind of has to be if we control L1 distances, I think. So this term here on the right, so this term here, if G is unequal to G tilde, would be strictly bigger than 0. And then also here, this distance would need to be strictly bigger than 0. So in this sense, I think, yes, it does. It is strictly positive for different points.
Thank you. Maybe I have one question. So do you recover the quadratic case of Conforti and co-authors?
Yeah, good question as well. So no, I don't actually recover this. So what Conforti and co-authors are basically dealing with is the case where here this decay of the cost function is of order 2, And also here, these exponential tails of the marginals are also of order 2. But delta is, so to say, 0 for them. So I call this a critical case, because here this rate of decay of the marginals and here the growth of the cost, these are of the same order. This is what they deal with. And the restriction that they are facing in this regard is that they can actually only show this exponential convergence then for large enough regularization parameters epsilon. And basically, I think they are dealing with this case already very elegantly and yeah, let's almost say conclusively. So I instead wanted to focus on this case where there's a bit of slack between these rates here, and but therefore also we can get the stronger conclusion that the convergence actually holds for all regularization parameters. But yeah, in this sense, I don't recover this. It could be recovered, but I don't think I would quite get back the same level of generality as they obtain in this case.
Thank you. And talking about this, you know, when you send epsilon to 0, which you don't do, but the constant A that appears here, do you have any feeling how it probably blows?
Yeah, so it's actually not the constant A that's the problem. It's this contraction coefficient kappa, which is the problem. So this constant A, I think, stays constant even if epsilon goes to 0. But this contraction coefficient kappa goes, let's say, exponentially fast to 1 for epsilon to 0. I haven't calculated it specifically, but I'm pretty sure that this is the case here as well. I mean, yeah. I think this is just a basic consequence of this, of using Birkhoff's contraction theorem, that there the dependence is just, yeah, kind of exponential.
Okay. Thank you. We have time for questions.
Yeah. I hope it wasn't too quick, the presentation.
Yeah, I have a question. So congrats, first off. I think it's fantastic work.
Yeah, thanks.
I think a lot of people have been trying to make this work for a long time, including, I remember at least one paper where the authors were dealing with this for bounded functions, and they were somewhat explaining why they think that one cannot make it work for unbounded functions. So it was something topological about cones having empty interiors and such and such. So first of all, it seems that you have somehow managed to get rid of this obstacle.
Okay.
Can you say something about how your solution relates to their comments, or somehow topology doesn't play a big role in your view anyway?
Yeah, I mean, I hope I didn't violate anything which shouldn't work. But
no, it wasn't like a theorem or something.
Yeah,
it was more some hand wavy.
Yeah, I mean, I see, what I see is really that this L infinity version, let's say this baseline version of Hilbert's metric, this shouldn't work in these unbounded settings, because there, let's say you would have to, I mean, in theory, this version could also work, because it could happen in theory that all iterations of Synchron's algorithm have precisely the same rate of growth. So in theory, you could really evaluate this L infinity version along these iterations of Synchron's algorithm. Maybe their comment referred to that cannot work, because in a way, this is a very, let's say, sparse set of functions where this can work, and maybe it was something along these lines. But here really, for this new version, I don't know, it's really very general in the sense that a lot of things are finite. So you can have really a lot of functions of different growth, and the distance is still finite. So, yeah.
Yeah. So if I understand correctly, for instance, if the cost is like x to the p, distance to the p strictly less than 2, it works for sub-Gaussian marginals. or if the exponent is 2, it works for sort of strictly sub-Gaussian, slightly less heavy tails than sub-Gaussian.
Yes.
Is that right?
Exactly. Yeah, I just need a bit of slack. So in theory, everything that I'm doing could also be stated here without this delta. But then I would, as in the paper by Conforti, I would really have to pay attention to the regularization parameter. And this I didn't want to do in the sense because this is quite technical, and the best thing that I can do is recover or roughly recover what they did already in this most interesting case. So yeah.
Okay, so for a fixed regularization parameter and quadratic cost, your result would actually apply for sort of sub-Gaussian marginals if the sub-Gaussian norm is small enough, like basically the variance parameter of the Gaussian, so to speak, is small enough.
Yes.
Oh, okay. So but then doesn't that mean you basically fully recover the result?
Yeah, but I think actually my bound on this sub-Gaussianity constant is worse than theirs.
Oh, okay.
Yeah. But yeah, other than that, I think
it's some number. Yeah.
It's some number. Yeah.
Okay. Thank you very much.
Yeah. Thanks.
Maybe it's me not understanding it quite correctly, but so you want your Hilbert metric to differentiate between 2 points, right? So
yes.
This should depend on my test functions, right? Like I need to have at least enough test functions that it differentiates. Is that clear that your choice differentiates?
Yeah, I mean here, this is basically here in this theorem, this would be this condition. So we need to see at least something in the tails. Okay, so this alpha, of course, if alpha would be 0, then these functions alpha could just be, they cannot put any mass in the tails, and then of course we do not see the tails at all.
Yeah,
but here, this condition that we need to put some mass into the tails, then really allows us to separate these functions.
Okay, thanks.
Yeah. Very good question, yeah.
Yes. Are there any more questions? Well, then maybe we have had already plenty of questions, and we can stop here. And I would like to thank you, Stephan, and also Marcel, for these very, very, very nice talks, and for accepting giving a talk in this seminar. And I say goodbye to everybody. Thank you.
Yeah, thanks again.
Thank you, Julio, and thanks everyone for attending, and happy holidays.
Happy holidays. Thanks very much for the talks.
Have a good end of the year, everybody.